Hello, welcome to my video on data structures. This is part 7 of the hash table module. In this video, we will discuss the universal hash function. As we have seen in the previous videos, the design of the hash function plays a central role in the hash table data structure. Specifically, the constant time insertion, deletion, and search of data elements from the hash table relies on two fundamental properties of the hash function. First, the hash function should be computable in constant time. Second, the hash function should distribute data elements across the entire hash table evenly. The first property is relatively easy to satisfy, where we just need to make sure that the number of computing steps does not go up with the number of data elements. The second condition would need a little bit more consideration. Let's first look at what we would expect for a hash function that distributes the data elements evenly across the entire hash table. Denote two non-identical hash keys as x and y, the hash function as h, and the hash table size as m. Imagine that we have first inserted x into the hash table, and now we are trying to insert y. If we have a good hash function, then the location where y will be inserted should be independent of that of x, as x and y are non-identical hash keys. Since x has been inserted and occupies one hash table location, then the probability that y will also be hashed into that location by a good hash function should not exceed 1 over m, which corresponds to the expectation of even distribution of hash keys. In this case, we can claim that the hash function distributes data elements evenly across the entire hash table. Now, let's look at the definition of the universal hash function. Consider a function class h. A function class is a set of functions with the same form but different parameters. For example, the two functions y equals to 2x plus 5 and y equals to 10x belong to the same function class y equals to ax plus b, where they take different values for the parameters a and b. With that, we say a function class h is universal if for two different hash values x and y, the number of functions h from the function class h that makes hx equals to hy is no more than h over m. Here, the cardinality of h means the number of possible members in the function class. In this case, if we randomly pick a function from a universal hash function class, then the probability we make hx equals to hy is no more than 1 over m, which is what we expect from a good hash function that evenly distributes the hash keys. So, we can easily conclude that if we have one element in the table already, then the chance of a collision is no more than 1 over m. We can further generalize the conclusion that if there are n elements in the table, then the chance of a collision is no more than n over m, which is the low factor. Once we have definition, we can come up with a function class and prove that the class is universal based on the definition. While the proof can be important in theory, for application purposes, we only need to know which function classes are universal and implement our hash table by choosing hash functions from them. One known universal hash function class is shown here. Given the hash key x, we first compute its linear mapping ax plus b, and then compute the modulo of p, a parameter we can choose, and finally compute the modulo of m, the size of the hash table. In this function, There are three parameters whose values need to be determined, which are a, b, and p. We have several restrictions on the values of these parameters can take. The parameter p needs to be larger than the largest input key. Hence, we need to first estimate the largest value for x before determining p. The parameter a needs to be larger than 1 but smaller than p, while the parameter b needs to be larger than 0 but smaller than p. Once all these conditions are met, the corresponding hash function is universal. Now, assume that we have determined all parameters, and we proceed with implementing the universal hash function. We can simply implement it using the code shown here. Note that we would need to cast the variable type to avoid data overflow. Other than that, it is very straightforward. However, the naive implementation has one issue. That is, we need to compute two modular operations. While computing modular operation is expensive, computing 2 for each hash value could significantly slow down all associated operations. To be precise, it won't affect the time complexity, but it will correspond to a larger constant and lead to a slower wall clock time. Luckily, we can use a trick to reduce the number of modular operations to 1 from 2. The trick begins with assigning p as a Mersenne prime, which is defined as a prime number that can be written in the form of 2 to the power of k minus 1, where k is a positive integer. For example, 31 is a Mersenne prime as it is a prime number and can be written as 2 to the power of 5 minus 1. Also, note that p needs to be larger than the largest hash key. We claim that when we select p as a Mersenne prime that is larger than x, we can compute the corresponding universal hash function using only one modular operation. Let's see how this trick will work. We begin with labeling ax plus b as y and y modulo p as r. Our goal thus becomes to compute r. Based on the definition of Mersenne prime, we have p equals to 2 to the power of k minus 1, or we can write p plus 1 equals to 2 to the power of k. Now, imagine if we are dividing y by p plus 1. Because p plus 1 is an exact power of 2, it will allow us to compute the quotient and remainder of y divided by p plus 1 using bitwise operations. Specifically, the quotient can be computed by shifting y to the right by k digits, and the remainder is simply the last k digits of y. For example, consider the case of computing 7 divided by 4. We can easily find that the quotient is 1 and the remainder is 3. Let's see how these numbers can be computed using bitwise operations. We know 4 is 2 to the power of 2, and therefore in this case we have k equals to 2. In the binary system, 7 is written as 0, 1, 1, 1. In this case, shifting 0, 1, 1, 1 to the right by 2 digits would give us 0, 1 as a binary, which is just 1 as a decimal. It is consistent with the quotient that is directly computed. To find the remainder, we will simply take the last 2 digits of 0, 1, 1, 1, which gives us 1, 1 as a binary and 3 as a decimal. This is also consistent with the remainder that is directly computed. You can verify this computation with other numbers. Note that these bitwise computations are highly efficient, as most of our computers use the binary system internally. Once we have computed the quotient and remainder of y divided by p plus 1, denote them as q prime and r prime respectively. In this case, we can express y as q prime times p plus 1 plus r prime. Recall that our goal is to compute r, which is y modulo p. Substitute y with q prime times p plus 1 plus r prime. We can write r as q prime times p plus 1 plus r prime modulo p, which can be further simplified as q prime plus r prime modulo p. Consider the computation of q prime plus r prime modulo p. We know that r prime is smaller than p since it is a remainder of division by p plus 1. For q prime, recall that it is the quotient of y divided by p plus 1 and y equals to ax plus b. Since all a, b, and x are smaller than p, we have y less than or equal to p squared. In this case, q prime is less than or equal to p. Taken together, q prime plus r prime is less than 2p, which means we can compute its modulo with p without using an actual modulo operation. Specifically, if q prime plus r prime is larger than or equal to p and less than 2p, the modulo result would be q prime plus r prime minus p. Otherwise, the modulo result would just be q prime plus r prime. Taken together, we have shown how to compute r using a series of bitwise operations and a subtraction and avoid the use of direct modulo operation. The above computation trick is due to Carter and Wegman and is called the Carter-Wegman trick. The corresponding implementation is shown here. Here, the variable np corresponds to the parameter p, and digits correspond to k. In line 6, the two parts at the right-hand side of the equation shows the computations of q prime and r prime respectively. Line 7 computes r, and line 8 directly computes r modulo m as the only direct modulo computation applied in this function. In summary, we have discussed the definition of the universal hash function, we have given an example of a universal hash function family, and we have presented the implementation trick for its computation. In the next video, we will discuss two ideas that can ensure worst-case O1 access time. Thanks for watching and see you next time.